Okay guys, welcome back to another video. Today we are going to look at the principle of mathematical induction again. In the previous video, I have shown you that if we have S, which is a subset of a set of natural number, and S equal to set S if and only if we have 1 in set S, and if we have n in set S and then n plus 1 in set S. Okay, according to the previous video. And if we have 1 in set S and if we have n in set S and n plus 1 in set S, it can imply that set S is a set of natural number. This is the principle of mathematical induction in which we proved in the previous video. Today, we will take a look at the first mathematical principle, induction. Okay? But I want to go to this note first. So when we prove or give a reason for theorem in number theory, there are two important principles. The first one is well-ordering principle. It says that every subset of a set of positive integer has minimum integer. Okay, this refers to well-ordering principle. The second one is the mathematical induction, which is a proof for theorem or propositions or result which are true for every natural number n. Today, we are going to prove this theorem, which is the first mathematical induction. So we let P of n be a statement. The statement that we will show that is true for positive integer n. Okay? If we can show that P of 1 is true, it is the case that n equal to 1 is true. And the second one is if pk is true, then pk plus 1 is true for any integer n. If we can show that p1 is true, and if pk is true, then pk plus 1 is true. If we can show these two statements, then we can conclude that P of n is true for every natural number n. Now let's prove this theorem. Okay, let's prove this theorem. So let's start with this. So I gotta let P of n be a statement. Be a statement. Okay, for positive integer n. Okay, starting from 1, 2, 3 and all the way and so on. And we will assume that these two statements are true. So we assume that. I gotta write statement 1 and statement 2, okay, are both true. Okay, assume that these statements are both true, and I will do something. I will define this set. Since we want to show that if the first statement and the second statement is true, then Pn is true for every natural number n. So we gotta write this set, which is set S, a set of natural number, such that P of n is true. Okay. Then I'm gonna try to show that this set n is a set of natural number, because Because when it is a set of natural number, this means that Pn is true for all natural number. Okay, let's get started. So from 1, what do we have? From number 1, according to number 1. Okay, P1 is true, right? P1 is true. Okay, since P1 is true, this means that 1 is in set S. That's it. Hence, 1 is in set S. Okay, and P2, not P2, actually is the second statement. From the second statement being true, what do we have? Okay, we're gonna have if PK is true, implying that PK plus 1 is true. Okay, or any positive integer k. Okay, what does it mean by this? It means that k is in set S, right? Implies that k plus 1 in set S. It looks like we have the principle of mathematical induction right here, okay, in theorem 1.1.2. So 1 is in set S here, and k in set S implies that k plus 1 is in set S. Therefore, if we have this assumption, by the principle of mathematical induction, which is theorem 1.1 or 1.2.1, okay, which is the principle of mathematical induction. From this theorem, we're gonna have set S equal to the set of natural number. So right now, we're gonna have this set S becomes a set of natural number. Okay, so what does it mean by this? This means that Pn is true for all natural number n. Okay, so if this becomes a set of natural number, it can be implies that P of n is true for every positive integer n. Okay, so that's what we have, and this is the first principle of mathematical induction. So from now on, we can prove theorem in number theory by using the first principle of mathematical induction, especially with statement for positive integer n. For example, the statement might be like this: prove that 1 plus 2 plus 3 all the way to the n is n times n plus 1 over 2. We can use the first mathematical induction to prove it. Or you may have to prove this one: 1 plus 3 plus 5 all the way to n plus 1 minus 1 equal to n squared, which is true for every positive integer n. Okay, so that's it for today, and in the next video we are going to prove this example by using the mathematical induction.